a rising senior, and during my time here at SHINE under Professor Luhar in the Fluid Interactions Lab, I have designed, developed, and tested a low-cost spirometer, a device which works to measure patient lung function through a variety of criteria. One of the main reasons I've been doing largely medically oriented work in the aerospace lab is due to the massive overlap they share in airflow physics. Despite the vast mechanical differences between designing, for example, an aircraft and designing a spirometer, engineers working on each find themselves using the same equations because the same rules apply when dealing with airflow. This overlap is what led me to choose to work on designing the low-cost spirometer. It brought in plenty of hands-on work that allowed me to apply the theoretical knowledge that I was simultaneously learning. All great projects start somewhere, and for me, this somewhere was Wikipedia. I first had to learn the basics of the design. What I initially learned is that a key aspect that spirometers, specifically Venturi spirometers, function on is the Venturi effect, which essentially is just a fluid property where a fluid will be at a higher speed and a lower pressure at a point where the flow is constricted. Design-wise, this translates to creating a converging-diverging geometry, and a means to measure these 2 points in order to get a pressure differential. I did all the CAD design on Autodesk Inventor following these basic principles, and simultaneously designed the spirometer with the production method in mind. After my initial design, I optimized the layout to reduce turbulence, but the overall design stayed pretty similar. Another big part of designing the spirometer was actually producing it in physical space. I did this through the use of a 3D printer. The main thing you have to be cognizant of when 3D printing is reducing overhangs. However, aside from printing the whole spirometer in multiple distinct parts, there is no great way to reduce the overhangs found on the pipes. So the biggest challenge in the production process was optimizing the support for the overhangs so there was enough to successfully allow the pipes to print, but not too much to clog the pipes. Right now I'm at the point where everything on the spirometer is working fairly well, and I'm able to get some pretty interesting and useful data from it. The main way in which I focused on presenting the raw pressure data was through milliliters per second, or airflow volume. This was calculated by the code, which took into account Bernoulli's equation to convert the differential pressure into airflow volume, usable in metrics such as expiratory reserve volume and tidal volume of one's lungs. However, it took a lot of code writing, tweaking, and most importantly learning to get it here. Luckily, my PhD mentors Shilpa and Andrew taught me through that process. On the way, there were plenty of errors to solve. Out of everything, though, the most annoying error was definitely the fact that the spirometer would just stop loading data inexplicably every time I wanted to show it to Professor Luhar. Going through and solving these errors made me realize that even in research, you don't always have a clear solution, and sometimes you just have to throw things at the wall until they stick. Overall, Shine helped teach me that the whole point of research is that you don't always exactly know the next step. But the important thing is that you just keep trying to solve what problems you do know of until you find out about the ones that you don't, and then just go from there. I want to thank Professor Luhar, my mentors Andrew Javaran and Shilpa Vijay, my lab mates, all the great people I met, of course my family, and finally I want to thank Dr. Mills, Kathalina, and the rest of the Shine team for setting this whole program up, and then finding a way to safely run it amidst a global pandemic.